Hello?
Hello, Paulo.
Yes. I have to put the final instructions in the internet, okay?
Okay.
3 minutes.
Paulo?
Yes. Yes, in the beginning of the program, I have to speak something in Portuguese, okay?
Okay. When I go through the slides, I go through them fast, so just be ready to keep hitting the next slide.
Okay. And after I speak something in Portuguese, I would like you introduce yourself as your experience with nanotechnology.
Okay.
Okay, and after this you can start your presentation.
Say that again?
No, one moment please. I have to final instructions here.
Okay.
Let's see here. Bom dia, boa tarde, boa noite aos internautas que nos acompanham neste programa Nanotecnologia do Avesso. Hoje, o seu número 477. Fazemos este programa dedicado ao público não especialista, porque é este público que paga as pesquisas sobre nanotecnologia realizadas no Brasil. Também fazemos este programa porque é aqui que nós podemos discutir os impactos da nanotecnologia na sociedade, no meio ambiente, na economia, na saúde, nos trabalhadores, coisa que não são discutidas aonde se faz nanotecnologia no Brasil. Por fim, fazemos este programa porque acreditamos que ser livre é ser bem informado. E a divulgação científica contribui e colabora para o aprofundamento da democracia e da cidadania no Brasil. Hoje, conforme tínhamos anunciado, estamos conectados com o Dr. Paul Schulte, diretamente da cidade de Cincinnati, nos Estados Unidos. Ele é diretor de Informação e Educação da NIOSH, e nós vamos então passar a palavra a ele para que ele se auto-apresente e depois vai iniciar a sua conferência de hoje. Ok, Dr. Schulte, could you please introduce yourself?
Well, thank you, Paulo. It's a very big pleasure for me to be here and to speak with you today about nanotechnology. As Paulo said, my name is Paul Schulte. I am the co-manager of the NIOSH Nanotechnology Research Center and have been in 2004. We do a lot of different kinds of work in terms of research and development of guidance at the NIOSH Center. I'm also the director of the Education and Information Division at NIOSH. My training is in toxicology and epidemiology, and I look forward to speaking with you today, giving you an update on the health effects and risk assessment and management of engineered nanomaterials. Next slide, please.
Okay. You want the second slide or the first?
Say again?
Yes, if you want the slide number 2.
Number 2, yes.
Okay, it's in the screen. Okay, you can continue. It's in the screen.
No, I cannot.
No, you will not see these slides.
Yeah, it would be helpful. I have them here, but if I can't see them, if other people can see them, I will just continue.
Yes, you have to see the slide in your computer. Okay, okay.
I cannot see the slide.
Yes, you have to see by your computer.
Just a second.
Okay, there is no problem.
Is there something I should do on my computer, Paulo?
Yes, you can open your PowerPoint in your computer.
Paulo, you're saying open the PowerPoint?
They open PowerPoint?
Yes, open the PowerPoint in your computer. Okay, Amanda, you understand? Is to open the PowerPoint in the computer of Dr. Paul.
You're saying you want to send it to me? Through Skype?
We're opening the PowerPoint.
Yeah, because you will see the PowerPoint in your computer, not here.
Right, okay.
But you actually have the copy of the PowerPoint.
Yes, I have the PowerPoint here in the screen. For our audience, not for Dr. Paul.
Paulo, you can see the PowerPoint in your participants.
I can see here with my copy that I put in the screen here. Okay, you send me the copy of the PowerPoint. You have to open it.
We cannot share this control.
No, but it's not share. It is not share.
Right.
It's only open the PowerPoint in your computer. Only this.
Can you show the slides to your audience, Paulo?
Yes, I can show this slide for my audience.
Okay, so show the slides, and I will just go with my paper copy and tell you when to switch them.
Okay, I put the second slide, presentation.
Say again?
I put in the screen, the second slide is the presentation, the topics of the presentation.
Okay, should I begin?
Yes, you can do it. You can continue.
Okay, thank you. Today I will try to cover 5 areas related to engineered nanomaterials. I'll give you an overview of nanotechnology. While I know Brazil is a major powerhouse in development and use of nanotechnology. There may be some in this audience who aren't familiar with it, so I'll give you a brief overview of it. I'll do an update on worker health effects. I will talk a little bit about the status of risk assessment, address some issues in risk management, and then begin to show you the area of additive manufacturing and advanced manufacturing where nanomaterials will be widely used. So next slide 3.
Okay, is in the screen.
Okay, I don't see. Good. And then the next slide is the overview of nanotechnology. I'll go to slide 4 to tell you that what we're talking about with engineered nanomaterials is generally a phenomenon that has come about in the last 20 years, with notable exceptions, and I'll point some of them out as well. Next slide.
Okay.
Slide 5.
Okay.
So as I said, engineered nanomaterials represent a new and emerging technology. Generally, they have been in commerce since the early 2000s. We're talking about materials that have at least one dimension that's less than or equal to 100 nanometers. Now that 100 nanometer cut point is only a subjective mark for commercial and scientific categorization. When we think of particles, there's a continuum from the smallest particle to the largest particle. And all along that continuum, we see various kinds of health effects and biologic effects that give us concern. So the 100 nanometers is an arbitrary cut when I'll talk more about that. Engineered nanomaterials are not only so because of their size, but also because of their novel scientific properties. They have great commercial and scientific utility, and from what we could have anticipated in the early 2000s, because of, and I'll talk about this, air pollution epidemiology and other sources of information, we believe that they merit precautionary control because some of them could be hazardous. And if you go to slide 6, you'll see the basis for the information that gave us, that made us be concerned. One was that from air pollution epidemiology, particles less than 2.5 micrometers, and even ones less than 100 nanometers have been shown to be associated with respiratory and cardiovascular effects, including mortality. And so this is a major concern. Secondly, we know from looking at industrial fumes that are not engineered necessarily, but that are of the same size, for example, welding fumes or diesel fumes, we see a wide range of effects, including pulmonary and eye irritation, fever, and lung cancer. Also, some studies of engineered nanoparticles have shown that they can translate from the nose to the, translocate from the nose to the brain, up along nasal ganglia. And so this gave us concern because we know that particles that can get into the brain can be problematic. So from these three sources of information back in the early 2000s, agencies around the world issued precautionary guidance about nanomaterials. So what are these nanomaterials and what gives nanoparticles such great value? If you go to the next slide, page 7, you'll see that an example that will illustrate some of the properties. You can have a piece of gold, a bar of gold, and you break it in half, you will still have gold. And if you break each one of those in half, you will still have gold, and it will act like gold. Finally, when you get down to a bar that is about 60 nanometers on a side, you break that in half to 30 nanometer bars, you all of a sudden have a material that has different scientific properties, different physicochemical properties, such as lower melting point. Gold, which has historically been non-reactive and non-catalytic, now becomes a useful catalyst. Gold is not gold at this size. It can be many different colors. It can have different conductivity and other physical chemical parameters. So because of these size changes, new properties emerge, and these are one of the aspects of engineered nanomaterials. On slide 8, you will see that there's another feature that drives the utility of nanomaterials. For example, if you have a bar of gold 1 meter on a side, it will have the surface area of 6 square meters. Surface of materials is where biological and chemical reactions take place, so it's highly valuable. If you take that 1 meter bar of gold and you break it to little bars with 1 nanometer on a side, then you have as much surface area from that 1 meter bar of gold broken up into 1 nanometer sizes as the area of the U.S. state of Delaware. And so you can see how another characteristic of engineered nanomaterials that makes it quite useful. If you go through this next series of slides, slide 9, you'll see that nanotechnology can be useful in almost every commercial area. Not only to make things faster, lighter, stronger, but to address critical planetary problems in terms of energy or food or water. So not only was this a technology that people were excited about because of its scientific and commercial applications, but also possibly because of its efforts to remediate planetary problems. One area in particular in the next slide, slide 10, shows a nano device near a tumor cell, a nano device that could be put into a person and could go to the source of disease, in this case a tumor, and sense it, monitor it, and possibly deliver therapeutic materials. So this is an exciting possibility. So nanomedicine is a great area of interest. And then finally, on the next slide, 11, you will see an experiment that was done where scientists moved around xenon atoms in a way that they could spell out the name of their company, in this case the computer company IBM, and this is indicative of the potential to move, to build from the bottom up and actually move atoms such that you could build things. And I'll talk more about this later. Now we can go to slide 12 and see some of the problems in talking about engineered nanomaterials and their potential hazards, because they're not all the same. This slide 12 shows zinc oxide nanoparticles, but they're all different shapes and sizes, and consequently they don't all have the same toxic potential. So the language fails us in some cases when we try to talk about and characterize the hazards of engineered nanomaterials. The hazards are not uniform across the universe of nanomaterials, and indeed, with all the physicochemical characteristic combinations, there are unlimited number practically of engineered nanomaterials, and we cannot characterize them all in the same way. If you go to the next slide, slide 13, you'll see just sort of another view, drawings of the different kinds of engineered nanomaterials, somewhat like you saw in the previous one, just shown with a little more detail. Finally, if we go over to slide 14, we can see some of the parameters, the physical-chemical parameters that could affect nanoparticle toxicity. And so different combinations of these can make different kinds of nanomaterials with different toxic potential. And then lastly, in this overview, on the next slide, 15, you're looking at the air exchange region of the respiratory system, the alveolar air spaces. And you can see that in some cases, the nanomaterials react with different cells there, or don't react, as the case may be, and in some cases can evade phagocytosis by macrophages. And they can also trigger immunologic responses that generate cytokines and create oxygen stress. In some cases, it's even possible that the nanomaterials can enter the interstitium and penetrate into the through the lung, and I'll talk more about that later. So that was just a brief overview. I know most of you are probably familiar with engineered nanomaterials, but if you weren't, that was a general overview. Now I want to give you an update on worker health effects. My focus is occupational safety and health, and so indeed that's what I work on, the health effects of workers. And if you go to slide 17,
yes,
you'll see what I'm going to address. Now there are many different kinds of engineered nanomaterials, but I'm going to talk about today an overview of the epidemiologic and animal data for the 9 most common nanomaterials that are in commerce. And here they're listed by the World Health Organization in a 2017 report by the volume of commercial tonnage. And so you can see carbon black and synthetic amorphous silica are far and away the largest, and then it decreases in size. In some cases, the research has been disproportionate to the commercial tonnage. Hence, there may be more research about carbon nanotubes and titanium dioxide than about carbon black and amorphous silica. But indeed, these are the true figures of the commercial tonnage. I'm going to go briefly through all 9 of these categories. And just to show you, this is more detail than you might want, these next 2 slides show you the search strategy. This was essentially an assessment of the literature. Figure 2 here, slide 18, shows the search for epidemiologic studies that led to eventually finding 27 studies that we included in the review. And the next slide, slide 19, is a search of the animal literature for those materials, and we found 79 studies to include in the review. So the first one is carbon black. Carbon black, you may be familiar with it, and you'll be surprised here maybe what I say. It's a generic name for a family of materials. They have a range of particle sizes from generally 10 to about 500 nanometers, but they agglomerate, or in some cases aggregate, to larger sizes. Now, you wouldn't generally consider carbon black to be a high-tech engineered nanomaterial. They're what maybe we would call, though they do have the engineered high-tech versions, and I'll talk about them, but we can track back carbon black for at least 80 years in commerce. And so we nicknamed these legacy engineered nanomaterials. They're engineered because to make carbon black, you have to have physical conditions of certain temperatures and pressures. And so in a sense, they are being engineered. And so we've started to go back and track some of these through their legacy history as well as through their contemporary history. If you go to the next slide, 21, you'll see some of the beginnings of the health information on carbon black. The International Agency for Research on Cancer, IARC, reviewed the epidemiologic evidence on carbon black and essentially classified it as a possible human carcinogen. And you can read their 2010 report if you would like a detailed appraisal of that. Carbon black also on slide 22 has a body of epidemiologic evidence that indicates that there are various non-malignant respiratory effects. These have been fairly significantly studied, particularly by investigators in the UK, and so there's a pretty strong case for non-malignant respiratory disease. Also, there's the beginning of finding in contemporary workers of decrements of respiratory function and the initiation of an immunologic response as indicated by the presence of inflammatory cytokines. Also, contemporary or animal studies of contemporary engineered nanomaterials also showed a consistent pattern of epidemiologic information. Okay, skipping slide 23, let's go to slide 24.
Yes.
Okay, slide 24 then begins the next material, synthetic amorphous silica, or SAS. It's an intentionally manufactured material that has no measurable levels of crystalline silica. We know how toxic crystalline silica is, natural crystalline silica. This is manufactured amorphous silica. The particles are less than 100 nanometers. It too has been in commerce for more than 60 years, and it too is, in a sense, a legacy nanomaterial, as based on the fact that it's been produced under specified physical conditions. If you go to the next slide, 25, you can see the different polymorphs of silica. The crystalline silica to the right we're not talking about, but we're talking about the amorphous, the synthetic amorphous silica on the left, and particularly down the ones that go through a wet process, or a thermal process, and form pyrogenic silica. And I'll talk more about that in a moment. If we go on to the next slide, 26, we can see some of the characteristics about synthetic amorphous silica. As I said, the primary particles are less than 100 nanometers. It also has the propensity to aggregate and agglomerate. It hasn't been extensively studied, though there is an epidemiologic record that goes back to 1932, but it didn't show much in the way of adverse respiratory effects. Certainly no fibrosis, and wasn't designed or didn't exclude other potential effects, COPD, emphysema, or cancer. So it's sort of a not well-documented record. If, however, we turn to slide 27,
yes,
and we can look at the more contemporary engineered synthetic amorphous silica. A study looking at workers in 14 factories in Taiwan, published in the last few years, did show a variety of different kinds of effects, reactive oxygen species kinds of effects, indications of oxidative damage, and indicators that would give us concern that there could be the potential for adverse respiratory effects in exposed people. This was borne out, if you look on the next slide, by some studies, inhalation studies in animals. But it showed that that the effects weren't as significant. There was partially reversible inflammation, there was some granuloma formation, but no kind of progressive fibrosis. Also, though, there was some concern in one study that synthetic amorphous silica nanoparticles penetrated from the nose to the brain. This hasn't been followed up yet as to its significance, but just on the face of it, that is not a good thing to happen. Also, fumed silica, you may recall, it's one of the pyrogenic silicas that I showed you, has been shown to generate cytotoxicity and pro-inflammatory effects in the lungs of exposed animals. So there is a beginnings of a story of some but not significant respiratory effects in animals. Then if you go over to slide 29.
Yes, it's in the screen.
Okay, good. This is an interesting case study. It was published in 2011. It involved 7 female workers in a print plant in China. They were exposed to silica nanoparticles in paints and other materials that they were making, and these nanomaterials were found in pleural effusion. They were all hospitalized, and they suffered significant pulmonary fibrosis and inflammation, and pleural granulomas were identified. This study has not been strongly verified, so people have not put a lot of credence in it, but I present it to you just for reference, and if we ever see something like this there were many other kind of reactive chemicals in this environment, so people are not sure, investigators are not sure to what extent the nanomaterials were causal in this, but it's in the literature, and there are a number of reports of it, so I mention it to you. We'll now go to the third most common material in commerce on slide 30.
Yes.
This is aluminum oxide. It's the third most used material by tonnage, yet we have no epidemiologic studies of it, of workers exposed to nano aluminum oxide. Studies of workers exposed to just regular aluminum dust, which include aluminum oxide and may have included nano aluminum oxide, have shown a variety of health effects from pulmonary fibrosis through asthma and chronic obstructive lung disease to lung cancer. But it's not clear to what extent any of that relates to nano aluminum oxide. We also know that ultrafine or nano-sized particles have been found in aluminum smelters and pot rooms. Again, we're not sure to what extent they are causal in any health effects related to aluminum. So the human situation with aluminum, engineered nano aluminum oxide is fairly meager. If you go over to slide 31,
yes,
you can see what we found with animal studies, and this is a study, a multi-dose study, very short term, 6 hours a day for 5 days, different doses of engineered nanomaterials, 10 nanometers on the side, and it showed dose-dependent pulmonary inflammation and cytotoxicity. So there is some concern that nano-sized aluminum can have adverse pulmonary effects, but this is really the only real documentation of it. And this is only for 6 hours a day. We don't know if the pulmonary inflammation resolves or what really happens. Moving on then to the next, the fourth mode, slide 32. Again, another large family of materials. This is barium titanate, and the various titanates can have different other materials with them. So they're in the form of AbO3. They're known as perovskites. They're used in solar and electrical equipment. They're quite valuable. But there is no documentation of occupational exposure or animal inhalation studies. It's curious that this fourth highest material in commerce has practically not been studied in either animals or humans. We go on then to slide 33, and this, in contrast to barium titanate, is a widely studied material. Titanium dioxide, used in everything from paint, white paints, to toothpaste, to the white cream and Oreo cookies, if you're familiar with them, and the many different other things, sunscreen, and so forth. And it's been in use since the 1920s. Again, we're going to see a material that has some legacy nanomaterial history, as well as a contemporary engineered nanomaterial history. Particle size plays a big role in its application, generally in pigments, and it's used throughout the world in white pigments, white paint. The pigment size is 200 to 350 nanometers. Smaller materials, less than 100 nanometers, are used in electronics and photocatalytics and various high-tech materials. Going over to slide 34.
Yes.
We can see the beginning. We can see what's known about the worker experience with titanium dioxide. And epidemiologic studies have generally shown little evidence of malignant or non-malignant effects, but particle size was never well documented in these studies. For the most part, it's believed that they were of larger size, that all the epidemiologic studies of titanium dioxide workers involved particles greater than 100 nanometers. But as I say, the particle size has not been well documented. In 2010, IARC looked at the epidemiologic data for cancer and found it to be inadequate. I do note for your consideration one study by Bofetta et al. That found an excess, 23% excess of lung cancer, but there was no exposure-response relationship, and again, in that study, particle size was not assessed. So it's a limited utility. If we go over to the next slide, 25, we can see some studies of workers exposed to engineered nanomaterials where the particle size was assessed to be in the less than 100 nanometer range. And these studies showed alterations of oxidative stress biomarkers in exhaled breath. And so indeed, we're starting to see with titanium dioxide the kind of changes that would concern us. There's also a variety of different studies on exhaled breath and a variety of different oxidative markers, lipid oxidative markers that have been found, and also high levels of urinary OH HDG and ISO 8 isoprostane in exposed versus control workers. So indeed, there is beginning to see, when you start to measure it and look carefully, biologic changes. Whether these changes are predictive of any adverse effects is one question. The second question is whether these changes are, we know that these changes are not specific.
And a variety of different oxidative markers, lipid oxidative markers that have been found, and also high levels of urinary OA, HDG, and ISO 8 isoprostane.
Although I was hearing myself rebroadcast back to me, but now it's stopped. Okay, let's move to slide 36.
Yes.
Again, some more studies of workers exposed to engineered nanomaterials showing biomarkers of lung damage. The first one was in workers packaging engineered nanomaterials. Again, these are essentially cross-sectional studies, so you cannot infer causality from them. But they do give you a snapshot of what could be occurring in workers. Now, in addition to effects, we're starting to develop with engineered nanomaterials in general, and titanium dioxide in particular, alterations in cardiovascular disease markers. And so we're concerned that not only are there changes in the pulmonary system, they during pulmonary function, but there could be implications for possible adverse cardiovascular. Now, in addition, again, these are just a few studies of cross-sectional studies of workers and not truly representative of the whole workers. If you go to the next slide, we'll see what the animal information shows on this. And it, in a sense, is a little stronger than the human studies. But again, these animal studies, some of them are lifelong bioassays. Particularly the studies of Heinrich and Lee do show that rats exposed to particles between 50 and 40 nanometers develop cancer, various kinds of lung cancer. The concern with titanium dioxide and with many poorly soluble, low toxicity dust is that you create in a sense, a dysfunction in the lungs, known as lung overload, and that leads to secondary genotoxicity as a mechanism for carcinogenicity. So it's not that the material is carcinogenic per se, it's that the material causes the immune system to respond in such a way that it creates reactive species that can be genotoxic and lead to mutation. And so lung overload is a possibility, but nonetheless, IARC considered that there was sufficient animal evidence to show, to classify titanium dioxide as possibly carcinogenic to humans. All right, we're moving on now to the next category. This is down the list of the top 9 nanomaterials in commerce, as shown by the World Health Organization. The next one is cerium oxide. And they have been increasingly used, cerium oxide nanoparticles, in a broad array of applications. But again, like many of the other materials, epidemiologic studies of the workers are lacking. Animal studies, however, show, again, a similar pattern that we've seen with other nanomaterials of pulmonary inflammation and various kinds of pulmonary pulmonary fibrosis, and granulomatous acid.
Yes.
I'm hearing talking, okay?
Yes.
Okay, moving on then to the next. So that's all there was on cerium oxide. So moving on to the next material on slide 39 is zinc oxide.
Yes.
Here again we see a body of no epidemiologic studies in the literature that we searched for. So there is not much experience of workers exposed to engineered nanomaterials. There is one study, and this was from the mid-90s, an experimental study where 13 healthy volunteers were exposed to metal fume, zinc oxide metal fume, with particles of about 60 nanometers MMAD, mass aerodynamic diameter. But they didn't see much in the way of pulmonary effect on pulmonary function. They saw a little increased specific airway resistance and elevation of some plasma markers. Zinc oxide or metal fume fever is a widely well-known occupational entity that's occurred in various metal workers who teach related processes, and so this was not a surprise. If we go to slide 40,
yes,
we see what we see with animal studies. Here they are exposed to engineered nanomaterials, 35 nanometers, various doses. Again, though, all the way through, there's very little in terms of in the short-term studies of pulmonary effects. And even in a 13-week inhalation study, subchronic study, there was minimal pulmonary cytologic or histologic change. So zinc oxide does not appear to have a major record of causing adverse health effects. Moving on then to slide 41.
yes,
We have beginnings of the one of the most widely studied of the engineered nanomaterials, carbon nanofibers. And they don't really have a historic antecedent. They're relatively recent. There is some history, but it's minor. It was never used in commerce per se. It's only since the 1990s that we see them. They have extraordinary mechanical, electronic, and other properties. They can be a fifth the weight of steel and 11 times the strength. So they're indeed quite strong. There are many different types. One estimate was that there are 50,000 different engineered carbon nanotubes in commerce. So 50,000 different types. So it's a hard area to characterize in terms of adverse effects. We can look at some of the, on slide 42, the adverse health effects.
yes,
In workers, and we see in cross-sectional studies, again, a strong pattern of reactive oxygen species, oxygen stress, and markers in the pulmonary system. No adverse health effects directly. On slide 43, we can see, again, in another study of workers, just a small number comparing exposed and non-exposed, various kinds of immunologic markers. And then when you drill down and you start to look at the expression profile of messenger and non-coding RNA, you start to see patterns associated with pulmonary inflammation and fibrosis. On the next slide, slide 44, this was a study of 12 plants in the U.S. Carbon nanotube manufacturing plants, nanofiber manufacturing plants, which showed the presence of carbon nanotubes in the sputum, showed various kinds of blood markers and indicators of systemic inflammation and the potential for cardiovascular dysfunction. Intriguingly, what we're seeing is that the carbon nanotubes get into the alveolar regions of the lung, and it's not that they get then into the systemic blood so much as that they send signals from there to the blood, and it mobilizes a variety of inflammatory cytokines and other potential proteins in the blood that then can cause plaque formations on vessel walls. So there is a body of literature that's growing that gives us concern about that effort. There's a number of fairly well done epidemiologic studies that are coming about. The NIOSH one was one, but here's some from Europe on slide 45. It shows comparison of age and gender matched workers that had early lung effects and immunologic effects that again show a consistent pattern of pulmonary problems or pulmonary adverse effects. Similarly, on slide 46, you start to see a similar pattern in another exposure and unexposure match control study. Going to slide 47, we see some of the animal studies that were found with animals exposed to carbon nanotubes and nanofibers. And we see a strong case made for pulmonary fibrosis. And indeed, NIOSH developed a recommended exposure limit for workers based on these pulmonary fibrosis studies in animals. Again, there's the crosstalk between the pulmonary and systemic circulation that I talked about. And we're concerned about the potential for malignancy. Now, as I said, most engineered nanomaterials, there's a range of types of engineered nanomaterials, particularly carbon nanotubes, and some are rigid and some are not rigid. One of the more rigid types, the MWC-NT7, or the so-called Mitsui 7, was identified by IARC as a potential lung carcinogen, but we have inadequate or limited evidence on most types.
Okay, Dr. Paul, before you start the silver nanoparticles, I would like to propose for you that he continues in another program. Start with this slide 48, silver nanoparticles, because I have some question for you about what you told for us until now.
That's fine.
That's fine. Okay, thank you. I don't have in-deep question for you, because I don't have sufficient knowledge to put some in-deep question. But one question that he tried to work here is about the costs to do one epidemiological study, in this case with nanoparticles. What you could tell for us about this?
Are you asking about the cost?
Yes.
The epidemiologic studies are quite expensive. First of all, they're quite difficult because it's hard to find a large enough sample of workers who have what's known as statistical power, the ability to determine whether you have a meaningful difference between an exposed and a non-exposed group. And so consequently, you have to go to many different plants to really get a large enough sample. Secondly, you have to be able to assess the exposure and characterize all the nanomaterials. So these studies are costing generally over $100,000 US to do a real good one.
Yes.
They're fairly expensive. There are ways to sort of try to decrease the cost And I could go into that at some point, involving trying to use smaller numbers of subjects and using historical or in-plant data in terms of characterization and exposure can sometimes be used, but they are fairly expensive to do.
Yes, but I see the nanotechnology initiative, National Nanotechnology Initiative budget, and there is year by year the government put $1,800,000,000 to develop nanotechnology. There is no money to do this kind of research.
Right. I think if what you're saying is that this is a big high-tech industry that's going to generate a lot of money and it's worth spending on these studies, if that's what you said, that's what I agree with.
So,
I'm not sure if I followed your question completely.
Yes, because here in Brazil there is so little money to do something in impacts of the nanotechnology or nanoparticles. No, the money is to produce new knowledge about new products or new process, but money for the impact doesn't have. And here our money is public money. In the United States is more or less 50 public, 50 the companies. But the part of public is very small part to do this kind of research, the epidemiological impacts.
I understand.
And the NIOSH doesn't have a budget for this.
Right. So one of the things that we did was that we, not just we at NIOSH, but we authoritative agencies all around the world have continually issued guidance that employers should control exposures even while we don't know what the health effects are. We have enough concern that employers should control exposures to very low levels, and so even if we can't develop the studies right away or know what the adverse health effects are, we can have some confidence that workers are being protected because of the guidance. Because if employers adhere to the guidance that we've put out. In fact, right now in the U.S., we are doing a survey of employers for all different types of nanomaterials to find out to what extent they are following precautionary guidance. And hopefully this will alert us to whether they have been, or whether there are some hot spots, some parts in the life cycle that need further guidance and further support. But indeed, it's costly to do these studies, but we need to eventually study these workers.
Yes, I agree with you. But it's easy to do this kind of research inside the companies.
Say that again?
I ask you if you think that it's easy to do this kind of research, epidemiological research, inside in the companies.
Is it easy to control exposures?
Yeah.
Yes, and in fact, that's one of the good features that we have found, that the classic methods of particles in air control, engineering control methods, respiratory, personal protective equipment, will work on engineered nanomaterials, even down to the smallest sizes. And we published a number of materials on that. And so while we don't know what health effects may be, we do know how to keep the levels low using classic methods that don't necessarily require expensive investment.
Yes, this is my question. What is the cost of this kind of equipment?
Well, the costs are not extraordinary. I can't tell you the precise cost because they differ for each location and type of material and situation. But they're the type, they're the range of costs that all employers who manufacture things that make dust that are not necessarily nano, just micro, are already spending. So it is not an exorbitant expense to control exposures to these materials. Plus, for the most part, these materials are so valuable that and often made in small amounts that manufacturers are more worried about losing the materials or having them contaminated by external sources, including the workers, that they already invest in closed systems that will keep keep workers safe while they also preserve the integrity of the materials. So this is this all comes down to the fact that it isn't too costly to control exposure.
And you can use only one equipment for different nanoparticles.
I'm losing it. I didn't hear that.
If you can use only one equipment for different kind of nanoparticles.
Yes, you can use, essentially, it's local exhaust ventilation can be used, area ventilation, and N95 types of filtering face piece respirators can be used. And they can be used for all different kinds of engineered nanomaterials.
And what is, in your opinion, the bottleneck in this kind of research?
What is my opinion of...
The challenges, the bottleneck in this kind of research.
What is my opinion of the control strategies?
Yes.
Well, I think they are... We've shown that they are effective. We've shown that nanoparticles won't penetrate a respirator, that the local exhaust ventilation can pick up small nanomaterials. So my opinion is that they are very effective. They are not that exotic, and hence can be used widely. And most ventilation engineers understand the aerophysics enough to be able to put them into place. So I think they're a great strategy.
Okay, thank you for your interview today. It's 4 p.m. and I will send you a mail to have another interview, the part 2 of your interview. You choose the date and he can do another interview.
Okay, that's fine. I enjoyed talking with you. I hope it was helpful, and I look forward to talking to you again. Thank you so much.
Thank you so much. Bye-bye.
Bye-bye.